Hello everyone, this is Group 12. We're going to show the cloud implementation. First, I will introduce the overall architecture. The pain points for existing application is performance, reliability, growth, and cost issues. To address these issues, we proposed a cloud-based application. We have three virtual private clouds to support Calendar headquarters and other offices in three regions. AWS IAM is used for security and logins, and AWS certificates and KMS are used for encryption. We provide domain name resolution services via Amazon Route 53. Network load balance is used as a unified request portal. It will automatically secure request processing capacity in response to entering point traffic changes. CloudFront is used to distribute content. AWS CloudWatch monitors utilizations and notifies autoscaling group if autoscaling is required. If there are any errors, it will also inform Amazon SNS to send email notifications to application administrators. We use a tied storage class approach for storage and backup needs, and we set S3 lifecycle policy to transfer objects between different storage classes automatically.
Hello all, I'm Yokesh, Solutions Architect, and I'll be presenting the overall VPC structure along with the subnets, NAT gateways, availability zones, security groups, and network ACL configurations. Now I'll start sharing my screen. There we go. Starting off with the VPC, as you can see here, main VPC is the primary VPC setup in the US West region with the CIDR block as mentioned in the initial report. Moving on to the subnets that were set up, we have facilitated them such that your product is always online in two availability zones. There are two web servers, two app servers, and two database servers in each of the availability zone, US West 1B and US West 1C. These subnets have also been set up with the CIDR that have been prescribed in the resources report. An internet gateway has been set up for the web servers to have internet access. Also, one NAT gateway per availability zone has been set up in the web subnets for the app and database servers to have access to the internet. Furthermore, we have created custom route tables. The route table for the web servers have a route that targets the previously created internet gateway for internet access, whereas the other two route tables for the app and DB servers have a specified route that targets the respective availability zone's NAT gateway for access to the internet. That's it for the overall VPC setup. As for the traffic security, we have created a custom network ACL and associated it with all 6 subnets. It allows only HTTPS, HTTP, and MySQL traffic into the VPC, but any type of traffic can go out of the VPC. To further scrutinize the traffic into and out of instances, custom security groups were created. First, I'll demonstrate how I created a security group. Let's say I'm setting up the web ELB security group. As the ELB is responsible for receiving requests from the users across the internet, I set up inbound rules that allow HTTPS and HTTP traffic from anywhere on the internet. But as you can see, I can set a custom source and set a security group to keep the traffic just between the subnets as well. This is useful when it comes to private subnets or servers, as I will show later on. Outbound rule is fine, and that's it. If I click the Create Security Group button, the specified security group is created. Likewise, I've created a total of 5 security groups, starting with the security group which is associated with the Web Elastic Load Balancer. This is the security group creation that I just demonstrated. After this comes the web server security group. This allows the same traffic, but only from the web ELB security group. Next comes security group, which is associated with the App Elastic Load Balancer. And this security group allows the same traffic, but only from the web security group. Next in line is the app server security group, and this allows the same traffic, but only from the app ELB security group. And finally comes the database security group, which only allows inbound MySQL or Aurora traffic from the app security group. With the help of these custom network ACLs and security groups, your product on AWS is safe and secure. The very same setup has been established on EU Center 1. As you can see, Europe VPC, 6 subnets across 2 availability zones, 1 internet gateway, 2 NAT gateways across 2 availability zones, custom routing tables, custom network ACL, and 5 custom security groups. Likewise with SA East 1 region as well, South America VPC, 6 subnets across 2 availability zones, 1 internet gateway, 2 NAT gateways across 2 availability zones, custom routing tables, custom network ACL, and 5 custom security groups. That's it from me. Thanks.
Next, we need to create the workstation on our newly created subnet. According to the architecture, we set 3 VPC in 3 different regions: United States, Europe, and South America. Because the service of GoGreen covers about regions all around the world, it could lower the latency to improve customers' experience. Data is isolated in different regions. In each region, we adopt AWS service in two availability zones. In each availability zones, one public subnet for web tier and two private subnet for application and database. Then we use auto scaling to manage and control web tier and application tier in different availability zones. The previous step has created a launch configuration, and in the earlier text, we have created target group and application and web load balancer. We can now combine all this configuration to configure auto scaling. Let us create an auto scaling group for application tier. In step 1, we need to set the auto scaling group name and choose the launch configuration we created before. In step 2, we select the VPC and all subnet of application tier. Well, in step 3, we need to set the load balance. For the first time, we need to create a new one, set the VPC and its subnet, then create a specific route for target group, turn on the CloudWatch as well, and in the step 4, it is about the group size. Here we set the maximum capacity is 2 and select the scaling policy. Here we set the target value is 60. In step 5, we turn on the SNS service to send a notification to specific email. In final step, we set a tag for search or filter. That is the detail about auto-scaling. Next, I will show you the detail of creating EC2. First, we set an EC2 name. Then, according to our report, we set the instance type as M4 large. Then we set a key pair according to the tier. Then about the network setting, choose the VPC and the subnet, and then set the auto assign public IP as enable. Then select the security group. This is all information of this EC2. Then we need to follow the architecture launch EC2 instance 1. After EC2 instance, we will implement auto scaling. First, we create the launch configuration for application and web tier. Here is the example. Set the configuration name and choose the AMI. Then select the instance type as M4 large. Next, use the CloudWatch to monitor. Then select the security group. Last, choose the key pair based on the tier.
Hi, so now we set up our Amazon S3 buckets to store data. So with Amazon S3, we pay only for what we use. We already set up our initial bucket, but let me walk you through the steps of some of the things we did earlier. So if we click on create bucket here, we can put a name for our bucket. And then for our object ownership, we go with ACL disabled, which is the recommended setting. This will protect our S3 bucket from public access. We also enable bucket versioning for our bucket so that we can store different versions of files that will be changed by the user or our application. To ensure that we protect data at rest, we specify the use of server-side encryption. The encryption key type can be managed by Amazon, or we can manage it ourselves with AWS Key Management Service. For simplicity's sake, we use Amazon S3 Managed Keys for now. And then we do click on Create Bucket. Now let's go back to the bucket we already created. We can upload files as needed. Our application can connect to our S3 bucket to upload items. Our database snapshots are also exported to our S3 bucket so that our recovery point objective can be achieved. For storage lifecycle, we can manage this under management. So we already created a lifecycle rule. Let's click on this. Our data is initially stored in S3 standard. After 90 days, it will be moved to infrequent access. And then after a year, it will be moved to S3 Glacier. And after 5 years, it will be moved to Glacier Deep Archive. Now we set up some additional components. One of the additional components we can set up is the Route 53 domain name service. Remember, we have backup web and application server set up. So Route 53 ensures that users are always routed to our website correctly, whatever web and application servers that we use. First, we need to have a registered domain name. Once we have that info, then we can set up routing internet traffic to the resources for our domain. If you don't have a domain name yet, don't worry, because Route 53 can also help you register your own domain. Okay, assuming we already have the domain name, then we can set up a public hosted zone for our Route 53 setup. So this determines how traffic is routed on the internet. After that, we can define our traffic management rules. We can use several routing policies. Okay, let's just show how it looks. Okay, so we can use several routing policies. In this case, you can create a geolocation routing policy so that the user is directed to the web server nearest the actual location of the user. This ensures that our website will have fast response times to the users. Route 53 can also check the health of our web servers. So that is something we can set up for you.
Now we're going to introduce the implementation of Lambda. This is a procedure of Lambda image resize. By Lambda, we can focus on code, and Lambda will manage the server. When the user uploads their picture to S3, the Lambda function is triggered. Then Lambda will run the resize function. Finally, the user will get the thumbnail. To achieve this, we create two buckets, one for uploading images and another for storing the resized images. We have uploaded an image into the bucket, and another bucket is empty. And now we're going to create a Lambda function. We choose to start from the scratch. We name the function, and we use Python to write the function. Then we choose IAM role. I have set up a role, which allows Lambda to read the file from S3. After creation, we first add a trigger. Our trigger is S3. We choose a bucket which stores the uploaded images, and the event type is all objects, because we want the function to be triggered as soon as there is a new object in the bucket. Then we're going to write the function. This code is combined with two functions, one for resizing images, and another is a main function which uploads the resized images to the specific bucket. We use environment variables so that we can easily change the bucket to store the resized image. We deploy the code and we set the handler to our main function. Before testing the code, we should add a layer. Because we use Pillar to processing images, and Lambda didn't provide this package, we need to add Pillar to Lambda running environment. There are two ways to upload the packages. One is to pack the code and the package together and then upload the zip file. Another is to upload the package to layer and reduce net time. We choose the second one. We provide an ARN. Then we're going to configure the test settings to run the test. We change the bucket name and ARN. Then we modify the key into the name of the image we uploaded. Finally, we can run the code. When we say succeed, we can see the running details. We will only pay for the running duration time to save the cost. We open the bucket that stores the resized image to see the results. We download the file, and we can see the thumbnail. This is the end of our presentation. Thanks for watching.